My name is Nikita Mutkure and my colleagues are Neeraj and Mazi. We are students of MSc first year Department of Physics from Rashtrasanta Tukadoji Maharaj Nagpur University. Today we are presenting our quantum mechanics topic, separation of Schrodinger equation in radial and angular parts. I hope you will understand it. Let's get started. This is our topic of today's presentation: separation of Schrodinger equation in radial and angular parts. This is very small topic of quantum mechanics, and our video is guided by Dr. Prashant Gade sir. Then let's get started. First of all, we need to know about Schrodinger equation. What is Schrodinger equation? The Schrodinger equation is the fundamental equation. Is a fundamental linear partial differential equation that governs the wave function of quantum mechanical system. It is a key result in quantum mechanics, and its discovery was a significant landmark in the development of the subject quantum mechanics. The equation is named after Erwin Schrodinger, who postulated the equation in 1925 and published it in 1926. The Schrodinger equation is the fundamental equation of quantum mechanics in the same sense as the Newton's second law of motion of classical mechanics. It is the differential equation for the de Broglie waves associated with moving particles and describes the motion of particles. He introduced a function psi, which is the variable quantity associated with the moving particles and is a complex function of the space coordinates of the particle and the time. Then today we are going to learn about separation of Schrodinger equation in radial and angular parts. Going through our first slide. In our first slide, to learn the separation of Schrodinger equation is need. Today we take a spherical coordinates because the particle is moving with respect to time and constant potential. Then our derivation first part is spherical coordinates, which is what is spherical coordinates? Spherical coordinates of the system denoted as r, theta and phi is the coordinate system mainly used in three-dimensional system. In three-dimensional space, the spherical coordinate system is used for finding the surface area. These coordinates specify three numbers: radial distance, polar angles and azimuthal angle. These are also called spherical polar coordinates. Cartesian coordinates x, y, z are used to determine these coordinates. We learn the conversion. Here, the radius is measured from a fixed origin. The polar angle is measured from an imaginary point near to the exact location of the azimuthal angle, and on a reference plane passes through the origin. The radial distance is also known as radial coordinate apart from the radius. The polar angle could be mentioned as a collatitude, zenith angle, normal angle or inclination angle. R is the radius of the system, theta is an inclination angle, and phi is an azimuthal angle. This is our please see our diagram, which is spherical coordinates. This is coordinate Cartesian coordinates x, y and z. P is a fixed point and r is a distance between origin to fixed point. Theta is a polar angle and phi is azimuthal angle. And our spherical coordinates are: the potential central force VR depends on the distance r between the proton and electron. or spherical coordinates, spherical polar coordinates is x is equals to r sine theta cos phi, y is equals to r sine theta sin phi, z is equals to r cos theta, and r is equals to under root of x square plus y square plus z square, and theta will be cos inverse z by r. This is a polar angle which is which is represented by theta in our diagram, and phi is equals to tan inverse y by x, which is azimuthal angle, and this is represented in our diagram is phi. Go through next slide. Spherical schrodinger equation. It is mainly in our next slide. The spherical schrodinger equation. It is important. It is important that it is important. The time independent schrodinger equation in spherical coordinates is commonly time independent schrodinger equation is del square psi r plus 2m by s square e minus v into psi r is equals to 0. This is a common time independent schrodinger equation, but here we take spherical coordinates. That's why we transform the common time independent schrodinger equation into spherical coordinates, and the equation is minus s square by 2m into 1 by r square del by del r into r square del psi by del r plus 1 by r square sin theta into del by del theta sin theta del psi by del theta plus 1 by r square sin square theta del square psi by del phi square plus vr psi is equals to e psi. This is difficult to solve unless we can find separable solution such that psi with respect to r, theta and phi is equals to r is radial coordinates, and y with respect to theta and phi is angular coordinates, which then gives we put the capital R to the radial equation, and y to the angular coordinates. The equation is minus s square divided by 2m into 1 by r square del by del r into r square del capital Ry by del r plus 1 by r square sin theta del by del theta into sin theta del ry by del theta plus 1 by r square sin square theta del square ry by del phi square plus vr capital Ry is equals to e capital Ry, and another represent the equation recreation of equation minus s square by 2m into y by r square. Here we y outside the bracket. Here we take outside the bracket y. Y is y by r square del by del r into r square del r by del r plus here we take outside the bracket is r by r square sin theta del by del theta into sin theta del y by del theta plus capital R. Here we take outside r, capital R by r square sin square theta del square y by del phi square plus vr capital R into y is equals to e capital Ry. Go to the next slide. Separation of variables. Here we this is our previous equation, which is dividing by ry, dividing by ry, which is coordinates of radial and angular, minus s square by 2m, and equation is minus s square by 2m into 1 by r capital R into r square del by del r into r square del r by del r plus 1 by y r square sin theta del by del theta into sin theta del y by del theta plus 1 by y r square sin square theta into del square y by del phi square plus vr is equals to e. After dividing this equation, by ry, the equation will be, and after we multiplying this equation by minus 2 mr square by h square, and bringing the e over 1 by r del r square into del r by del r plus 1 by y sin theta del theta into sin theta del y by del theta plus 1 by y sin square theta into del square y by del phi square minus 2 mr square h square into vr minus e. We e transfer from right side to left side is equals to 0, and finally we regroup the radial and angular parts. Here we already separate out the radial and angular parts. In red color we use red color for radial equation and blue color for angular equation, and our radial equation is 1 by r del r r square del r by del r in minus 2 mr square h by h square vr minus e. This is our radial equation, and our angular equation is plus 1 by y into 1 by sin theta into del theta into sin theta del y by del theta plus 1 by sin square theta del square y by del phi square. This is our angular equation is equals to 0. Since the two parts depends on different variable, left side has variable r and right side has theta and phi. Hence this equation can be correct only if both sides are equal to some constant. Let this constant be L. We take a constant to radial equation and angular equation, L into L plus 1, and we take radial equation is equals to constant which is 1 by r del by d by dr into r square dr capital R by dr minus 2 mr square h square vr minus e is equals to L into L plus 1. And to angular equation we take constant 1 by y into 1 by sin theta del theta into sin theta del y by del theta plus 1 by sin square theta del square y by del phi square is equals to minus L into L plus 1. We will first solve this angular equation because we take constant, but in angular equation two coordinates are there, theta and phi. That's why we solve the angular equation. Another separation of angular variables is 1 by y. We separate out the theta and phi equation. 1 by y into 1 by sin theta del theta into sin theta del y by del theta plus 1 by sin square theta del square y by del phi square is equals to minus L plus 1. And after that we begin by multiplying by y sin square. We have to multiply y sin square, then our equation will be sin theta del theta into sin theta del y by del theta plus del square y by del phi square is equals to minus L into L plus 1 sin square theta y. Rearranging this equation, sin theta del theta into sin theta del y by del theta plus L into L plus 1 sin square theta y plus del square y by del phi square is equals to 0. This is clearly separable into two angular variables by assuming y with respect to theta comma phi is equals to theta and phi, which is already discussed about polar angle and azimuthal angle. theta, with respect to theta equation, is a polar angle, and with respect to phi is a azimuthal angle. And our last equation is phi into sine theta d by d theta, sine theta d theta by d theta, plus theta phi L into L plus 1 sine square theta, plus theta del square phi by del d square phi by d phi square is equals to 0. Final separation can be achieved by dividing by theta with respect to theta, phi with respect to phi. We have to divide this equation by theta and phi with respect to theta and phi, and our last slide we achieve our result. Second angular separation constant is separate out theta and phi equation, and then the separation constant is taken to be m square. We have to take separation constant m square to theta equation, and minus m square to phi equation, and m square is equals to 1 by theta into sine theta d by d theta, sine theta d theta by d theta, plus L into L plus 1 sine square theta, and minus m square is equals to 1 by phi d square phi by d phi square. We know now have identified three separation constant of three-dimensional Schrodinger equation, each of which corresponding to quantum numbers and operator which commutes with the others. Here we take in derivation we take three constant E, L plus 1, L into L plus 1, m square, and operators are with respect to separation constant H, L square and Lz, and quantum numbers with respect to our separation constant N, L and M. In our last slide, this is our derivation, conclusion of derivation, separation of Schrodinger equation in radial and angular parts. This is our answer, result. I hope you like this video. Thank you. I hope you understand about today's topic, which is quantum mechanics topic, separation of Schrodinger equation in radial and angular part. If you like this video, please subscribe our channel and like and share. Thank you.